our first speakers are David Anenko from Continental, Victor Pal, also from Continental, and Jochen Seller from SVA. So with that, I'll turn it over to David. And please feel free to submit any questions through the chats. Panelists will try to answer them throughout the presentation as well as at the end.
So, hello and a warm welcome from Lindau. My name is David Anenko. I'm the head of IT operations at Continental ADC, and I was the IT project manager for Continental's supercomputer project. In the upcoming slides, I want to give you a short overview why Continental decided to build up their own supercomputer and how it relates to the Continental's Vision Zero. Later on, I will hand over to Victor and Jochen, who will make a more technical deep dive into our environment. So most of you, I think, will know Continental because of our tire business. Nevertheless, at the ADC, we are working in the area of advanced driver assistance systems, shortly named ADAS. We are developing cameras, lidars, and radar sensors, as well as the central control units and the respective driving functions like adaptive cruise control or emergency brake assist. Our products already improve safety on the road pretty tremendously. Nevertheless, as still we have around about 1.3 million people dying in car accidents per year. This is where Continental's Vision Zero comes into place for no fatalities, no accidents, no injuries. And this is where we say our job is done when we are here at zero. So to further increase the safety in a car and also on the road, more intelligent driving functions are needed. So this brings us to the use cases we identified for our supercomputer. The intelligent driving functions I mentioned before clearly need the introduction of AI into our products. Machine learning helped us already to come quite far in our existing products. Nevertheless, the new functions need deep neural networks to accomplish their goal. So to shorten the training times and especially being able to test out many different setups of our DNNs is a perfect field for a supercomputer. As a second use case, we are also working on the field of generating synthetic data for our test and validation environment. In the ADAS environment, we do need to test and validate all of our products based on driven kilometers, mainly in the area of 1 million kilometers and more. For sure, this does not happen in real life. This is where our software and hardware in the loop environment comes into place. And to feed our SIL and hills, we need a lot of data. At the moment, we do have a test car fleet driving around about 15,000 kilometers per day worldwide, generating over 100 terabytes of data a day. This needs to be analyzed, labeled, managed, which, and I think you can imagine, for sure generates a lot of effort. Being able to create all the necessary scenarios and also all the kilometers for our software and hardware in the loop environments by, so to say, just pressing a button helps us to get more efficient and shorten our time to market. Last but not least, we also found a way to do our existing simulations by using the tremendous compute power of the many GPUs inside of our supercomputer, which helps us also crunching down all the test kilometers needed in our projects. So, beginning of 2019, our AI competence center, and also our management have seen a lot of opportunities and possibilities in establishing our own supercomputer. A project team was put together with a challenging goal to establish the environment within 7 months. 7 months for finding the fitting design, not only for the compute environment, but also the ecosystem, like the high performance network interconnecting all compute nodes. Here we needed to answer such questions like, do we go with RoCE or RDMA? Deciding for the right storage hardware and architecture. Here doing many POCs to find out the best product and solutions for our use case. Designing also our AI-ready data center with all the special needs in regards to cooling and also power consumption. And up to finding the right partner to support us in the setup. So this is where we came across SVA, who not only impressed us during our tenders with new cost-effective architectures, but also in getting our InfiniBand environment implemented and helping us as IBM partner, getting our IBM Spectrum Scale ESS 3000 environment established and on full speed. At the end, in this short time frame, all of this was only possible because we had also a really awesome team with a can-do mindset. So this definitely helped us to overcome many unforeseeable topics, like also, for example, jeopardized delivery times. This spirit we also found in the team of SVA and IBM during the build-up of the environment, where everyone was pretty excited about being able to be part of building up such a powerful environment. So I don't want to keep the tension further that high, to keep you away from the operations hands-on and technical details. So thanks from my side, and I would like to hand over to Victor. Thank you.
Hello, everyone. I'm Victor Pa, working as a deep learning infrastructure architect at the moment. And I was contributing to this project as a solution architect. And I would like to talk to you about how we actually built and how we actually manage this infrastructure. This is like AI infrastructure as a code. So first, just a simplified receipt for HPC and deep learning infrastructure, how I imagine it. So for HPC, you need several computers, compute and service nodes, low latency, high bandwidth network, high-speed storage, and some scheduling. And additionally, for deep learning, you need some GPUs, NVLink, and also GPU direct RDMA to support both inside the node and multi-node distributed trainings. You can see this diagram from NVIDIA's white paper, which represents such an architecture with deep learning nodes and InfiniBand network and high-speed storage. So what was the approach for building this infrastructure? Firstly, use what you know and realize what you don't. Don't reinvent the wheel. Partners with knowledge and experience can help a lot and can shorten delivery times and increase success. Cooperate and gain knowledge from each other and discover the available knowledge inside the company and organize the cooperation inside the company. And this leads to success. Automate whatever and whenever possible. Really, the only way to manage such complex infrastructures on the long run is automation. And another very important thing is to define clear and simple processes. Be agile and avoid the overhead of bad processes. For example, we have a single README page in our Git repository that describes our development and deployment process for the infrastructure that's easy to understand for everyone who's using that repository. So about the concept. Build the infrastructure from a single Git repository. It's really useful to only have one repository or just a few, because too many small repositories can get overwhelming. For some features, we have some separate repositories, but really we have one main repository where we keep our Ansible code and everything related to infrastructure. Use industry standard technologies. As said, don't reinvent the wheel. Use what's available and what's widely used, and that is very useful. NVIDIA DevOps is a good reference for deep learning infrastructures. They have an infrastructure as a code repository. You can see the link, and there is a lot of useful things there that can be used to build such an infrastructure. We also used a lot of things, not everything. We have our custom setup, but this was really a great help. Use the NVIDIA GPU cloud standardized, up-to-date, tested images. This is also very useful. Use open source technologies where possible. This was really helping us. For example, the Cloud Native Foundation has an incubation and graduation process where that helps to decide which open source software is fits best for a purpose. Design and build for high availability and security from the ground up. These two things are really hard to implement later and much easier to implement when it is done from the beginning with this mindset. And another very important thing, have an as complete as possible test infrastructure, because with a complex infrastructure, deploying and testing changes is merely impossible if there is no test infrastructure for this. A few words about the journey. So as David already mentioned, we made a lot of POCs and reading white papers to understand all the concepts about AI and AI infrastructure. And it helped a lot that also IBM and others helped us with on-site environments. We were able to do installation on our own hardware and test the setup and test the performance. There were some hard decisions because there are good options on the market. And for example, one of the big decisions that we had to make is InfiniBand versus Converged Ethernet. And based on my experience today, I would suggest everyone who builds something like this to go with InfiniBand, because it's much easier to set up than Converged Ethernet. Consulting played a big role. Strong partners like SVA and also IBM helped us to build the InfiniBand network and storage very quickly. We made the experience, I have some experience with cloud, and we made the experience that cloud is much easier with infrastructure as a code than bare metal. Bare metal is hard there. This is where Foreman comes into picture, and Foreman helped us really to create a standardized, unified, and easy to manage bare metal infrastructure. Data center AI is somewhat special, so the cooling and power consumption are critical. And our experience was that NVIDIA's white papers and certified solutions helped a lot to decide and choose the right technologies. For example, IBM ESS 3000. And also at the end of the journey, we had to migrate all of our legacy all of the data on legacy storage to our high performance storage, and this was where we needed to think a lot and carefully design so that the users can continue their using their data without any interruptions. So going a little bit into detail about how we do this infrastructure setup and how we deploy our infrastructure. So as mentioned, we have our code on GitHub, and Ansible is using that code to build the infrastructure. What we first built is Foreman and AWX. These are two separate servers, two separate virtual machines provided by different departments, and we separated this from the main infrastructure so we can use these two to deploy the rest of the infrastructure, and this provides us the independency and the option to really spin up the whole infrastructure with these two tools. So with Foreman, we deploy all the servers or bare metal servers, and then with AWX, we deploy Kubernetes, and we use also with AWX Helm to deploy the rest of the stack on top of Kubernetes. For example, for storage, we use Rook and MinIO for serving data, also the Elk stack for logging, and Prometheus and Grafana for monitoring. And when all this is ready, on top of that, we can build the AI-based tools like Kubeflow, MPI operator, NVIDIA, and Mellanox device plugin. And on top of that, TensorFlow and PyTorch trainings can be run. We have a REST API that makes it possible for the users to start jobs on our cluster. And we also have a Jenkins that's a little bit of separated today that we use for building tools and some infrastructure tests. You can see the whole infrastructure here, the InfiniBand network, and also the storage, and also a simplified view of the software stack. And some words about why we use these tools and components. Foreman, as I mentioned, enables building bare metal environments automatically in a standardized way. AWX is very, very useful if one works in a team with Ansible, because it enables tracking, see what is running, logs, jobs preserved, and also prevent parallel runs where needed. And also pre-configured runs can be set up, and it provides a unified environment for both Ansible and Python. So it doesn't happen that someone's running with a different Ansible or different Python version, because it's always the same because of AWX. Jenkins helps us to easily integrate deployment, build, and testing of additional tooling that we need for infrastructure management. And Kubernetes, of course, is the state-of-the-art for scheduling and orchestrating today. It was originally built for stateless services, but currently the way to go almost in every area. But there is still a lot of development ongoing to make scheduling and deep learning right on Kubernetes. And for Kubernetes, we use the standard infrastructure as a code or package management for Kubernetes. It really, based on our experience, provides easy upgrades and easy deployments. So how does GPFS fit into this? I will start with the bad things. The initial setup of an ESS 3000 is time-consuming and it's complex. Upgrades at the beginning were very hard because it was a new product, but it's getting better. We are already seeing this with the newer upgrades, and we are hoping that the next upgrade will be very smooth. You saw our toolchain, and the GPFS doesn't fit into this toolchain easily, so it's hard to automate with our existing toolchain. This is why we decided to manually do the setup. but I heard good news that there is integration with Ansible and coming. So we plan to do this integration when these features are available. And we also experienced that support can be cumbersome at sometimes. And also to the good things. Stability, we haven't seen any hardware or any other issues or outages with GPFS. It's just working since we did the setup. It was easy to extend, add new enclosures. The performance is good, and the integrated monitoring system is very nice and is covering a lot of things. A little bit of additional details about our storage architecture. So for data ingest, we decided to go with the S3 protocol because it provides good access control. It's available from everywhere because it's HTTP, and we have a lot of control over our data structure. We can spin up different instances, and inside those instances, different buckets, and we can just manage what's where on the storage, who can access it, who can write to it, who can read it. It's really seems to be a good solution. It's a standard protocol. There's a lot of libraries available for all the programming languages. And why we did not choose the CES object store version is because we knew that we will be using a lot of functionality regarding object store, and we needed the freedom to integrate the new features with updates and keep up with mainline development. For data access, of course, inside the cluster, it's native GPFS over InfiniBand. That's the fastest. And everywhere else, also MinIO for accessing the data on workstations and laptops for deep learning trainings. And we also use CES for NFS and Samba because it's really easy to set up. We can provide workspace access to the users. They can just mount their workspaces on Windows, on their computer. Using NFS, we can easily make cluster component backups on GPFS. A few words about what we are working on currently. Regarding data and storage, we are working on moving infrequently accessed data to cheap storage. That's also a big advantage of GPFS, that this is really easy to implement. And also, we are working on improving this disaster recovery. Regarding the workflow, scaling out transparently, for example, to the cloud or other locations is one of our main goals. Also, refining scheduling and utilizing the resources in our cluster more efficiently is very important. Keeping up with the verge, updating and upgrading regularly, this is something that we think is really, really important, and we would like to invest time into it to integrate new features and improve stability. We are also working on providing a better and easier AI workflow and minimizing the developer overhead to start the job on the cluster. And of course, refining monitoring is a constant work, and this improves availability, helps with troubleshooting, and helps with discovering early issues earlier. Another thing that we are working on is fully automating our Jenkins and AWX installations. That means that not just the installation of those instances, but all the configuration of these tools should come from Ansible and should be built from Ansible. And last but not at least, we are also working on a more automated hardware management, like firmware management, firmware upgrades, and out-of-band management like iDRAC, ILO, and BMC upgrades, user management, configuration management.
Okay, thank you so much, Victor. And now transitioning to Jochen.
Thank you to David and Victor for all of these insights, and good morning and good evening to everyone here in the call. My name is Jochen Zeller. I'm an IT architect working at SVA, the powerful system integrator in Germany. During the next 15 minutes, I will talk about the storage of the deep thought project. Before I start, a few words about SVA. SVA is covering everything around data center I2, on-prem and co-locations and cloud. SVA is an excellent employer and growing very fast. I started 8 years ago. At that time, we were almost 300, and today SVA employs over 1,600 people and almost 1,000 technical experts. Back to the Deep Thought project. First, I would like to explain what are they doing from a very high perspective. They have stored a lot of images into the Spectrum scale file system. In a training run, images will be loaded into a neural network, and the network tries to recognize the content of an image. In this case, with a very high accuracy, red traffic lights, and derives a react like, yeah, stop would be perfect here. That's what they are doing inside. And this brings out the questions, why do they need ESS 3000 as an image repository and not a typical spinning disk-based storage system? Conti is using a huge number of tagged images and many GPUs in many DGXs. This enables Conti to run many trainings in parallel. Before a training can start, all required images must be loaded into the GPU caches. For example, A100 GPU has 40 gigabytes of memories. This means around about 80,000 images at a size of 500 kilobytes. Assuming that the images are read by a single process and the storage latency is 6 milliseconds, then loading of this 80,000 images would take 8 minutes. That's a really long time. For an NVMe-based ESS 3000, we assume 0.2 milliseconds of latency. Then loading takes only 16 seconds. This dramatically reduces the idle time of the GPUs during the data load process. The Conti HPC cluster is using 7 of these ESS 3000 storages in the backend. They have many DGXs and more than 20 HDR InfiniBand switches. The entire InfiniBand network is planned as a non-blocking network. All clients are attached by 100 gigabit EDR, but the inter-switch links are running HDR 200 gigabits. This reduces the number of inter-switch links and increases the number of leaf ports for the DGXs and the storage. And each DGX is connected with 4 or 8 EDR ports for storage and GPU communication. Let's do a deeper look to the storage. Each of the 7 ESSs is equipped with 24 NVMEs and 2 node canisters. Or in other words, the 2 node canisters are 2 x86 servers sharing the 24 NVMEs and running Red Hat Enterprise Linux 8. Each of the node canisters is equipped with 4 EDR InfiniBand ports. In total, the storage consists out of 168 NVMEs and 56 EDR ports. Next, I want to show you the ecosystem of the Deep Thought project where we use features of Spectrum scale. The only way to ingest new images into the cluster is the Object Storage Gateway MinIO. This is not really a spectrum scaled feature, but we decided to use MinIO instead of CES object, as Victor already mentioned. One of the key features of MinIO is that it's very easy to configure and to maintain. When new data is ingested, we run every hour a policy that detects these new ingested files. A rule of this policy turns on the immutability flag for each new file. In addition, the same policy run creates an AWS S3 copy of the new images by a TCT export. We use the TCT export function because this creates the same structure and object names in the buckets as in the file system. This makes it very easy to adapt compute jobs for the cloud. Each DGX is a spectrum scale client. This means that they are able to access the images by RDMA and spectrum scale protocol, which is very fast and low latency access. The trainings are running in containers on the DGXs. The containers are managed by Kubernetes clusters and accesses the images by a bind mount of the project file set. Next year, we want to take a deeper look to the container native storage, container native spectrum scale and CSI, and hope that and last but not least, developers can access the data by CS SMB protocol. Now let's have a look at the ESS 3000 configuration. We have configured one recovery group per ESS 3000 chassis, and inside this RG, we have 4 vDisks per chassis. We used RAID code AD plus 2P, and 2 vDisks will be hosted by each node canister. If a node fails, the other node will take over all vDisks, doesn't care to the cluster. In total, we have 28 vDisks and 7 ESS 3000, and all vDisks hold data and metadata, and all of them are assigned to the system pool. And we use only one file system with a file system block size of 4 megabytes. Why did we do this configuration? Yeah, we optimized this for the reading of images with a size of 500 kilobytes. During summer, we had the chance to do some performance tests on the cluster, and we get 8 DGXs for testing read and write from the ESSs. And this one you see here is a performance test with 500K blocks. When you take a look to the writes, they are not very, very fast. This is because of the small I/O size we used for our testing and the file system size of 4 megabytes. That's why we are just reached 24 gigabytes, but this is not so bad for this environment. But the entire system is used and optimized for reading the 500K images, and this is pretty fast here. We achieved 110 gigabytes per second with the 8 nodes, and the fastest node was reading with 15 gigabytes per second. Unfortunately, we did not have the chance to test with more nodes, but we expect to exceed the 200 gigabytes per second mark with the entire environment. Something about the ESS 3000. I have been working with spectrum scale and ESSs for a long time, but the ESS 3000 software stack surprised even me. What did you think? How many commands are needed to update 7 ESS 3000s, including the scale code, native RAID code, Red Hat, OFAT, firmware of the NVMEs, adapters, and servers? Now you could not answer, you just have a Q&A. Give me the answer. It's just one ESS 3K run. This is extremely cool compared to the previous ESSs and a good step into the right direction. And as Victor already mentioned, this would be very, very helpful to have this in the future for ESS and non-ESS spectrum scale environments to make installation, configuration, and updates much more easier. Now I have some words about why do you need an ESS 3000 in your environment? Sorry. And this is very easy to answer. It's to speed up your current spectrum scale file systems. The ESS 3000 is absolutely inexpensive compared to other storages that are able to run 40 gigabytes per second. You can use your spectrum scale policy to configure the ESS 3000 as a default ingest pool for all file creates. And once a day, or based on a threshold callback, you can migrate older and larger files to the capacity tier. And of course, large file projects can still create their files on the capacity tier. This will lead to a fast ingest tier, and the most small files will be kept on the performance tier. And last but not least, you could create file sets that are per fast tier. Yeah, and just to be sure I didn't say anything wrong about the pricing of an ESS 3000, I have some homework for you. Go and ask your IBM sales rep for an offer of an ESS 3000 with the 3.8 terabyte NVMEs, and then be surprised. Many thanks for your attention, and yeah, are there any questions unanswered yet?
There was a question in the chat actually about, could you make a few comments about your Rocky eval that led to choosing IB? You mentioned easier with IB, but could you provide a little more detail?
So I was not working on that. One of my colleagues was, but we were working also together with, I think, with someone from Mellanox, and it was really complex to set up with Kubernetes. So actually, the biggest issue was Kubernetes and Rocky together. There were some limitations that that were not overcome at that time by the solutions provided, and this was just the solution was provided by Mellanox at that time was just not working. And we worked on that, I think, for weeks, and we didn't manage to get it working. And we also talked with others, and we haven't found anyone who was able to make it working in Kubernetes, with multi-node trainings. So RDMA and everything between the GPU is working, and like InfiniBand was just working out of the box without any issues. Just the only thing that you actually need is the Mellanox device plugin on Kubernetes, and it just works like a charm. With Rocky, you need Motus and then additional network plugins, and it was still not working. So we were not able to find anyone who managed to get it working perfectly. It was kind of working in some situations, but compared to the easiness of native InfiniBand, it's just not comparable. At least it was not comparable at that time. And also, I think InfiniBand is a more mature technology also inside of HPC in general, and also inside of HPC. So this is what I can tell about this story. Any additional questions, just let me know.
Okay, thank you very much to our speakers, Johan, Victor, and David. If you have additional questions, please feel free to add those to the Q&A chat. Yes, and just a reminder that you can review past talks that the Spectrum Scale User Group has sponsored. Those are all available on the website listed on this slide. And also just a reminder, we have a session on Wednesday that will be on what's new in Spectrum Scale 5.1, as well as we'll have a panel where you can ask any questions about Spectrum Scale, a panel of experts. You can ask any questions and get answers. So yeah, and Spectrum Scale User Group is a great community, of folks working to help each other to use and optimize the use of Spectrum Scale. So yeah, we'd love to have you join us. There's information on the screen here.